Welcome back to the deep dive from Neural Intel. Today we're diving deep into some truly groundbreaking AI research. As always, our focus will be purely on the technical mechanisms and the groundbreaking engineering behind it.
That's right. We'll be exploring how these breakthroughs work rather than delving into broader societal implications today.
Exactly. And for those of you eager to stay updated on the latest AI and ML research, don't forget to visit our webpage, neuralintel.org, and check us out on YouTube. So let's set the stage. Imagine an AI that doesn't just, see an image. Imagine it can actively manipulate it, zoom in, enhance the contrast, maybe even rotate it.
Hmm.
And while doing all that, it's also crunching numbers, writing, and executing code to solve really complex problems. It's a huge leap beyond just thinking with images, isn't it?
It absolutely is. It sounds almost like science fiction, but as you said, it's becoming reality.
And the surprising facts behind how they actually built this thing are fascinating.
Indeed. We're taking a deep dive today into a paper that introduces a really novel paradigm for multimodal large language models, or MLLMs. It's called Thyme. Think beyond images.
Thyme, okay.
Yeah, and we're talking about models that basically transition from just passively interpreting an image to actively, intelligently solving problems using both vision and computation.
So it's not just understanding what's in the picture.
Exactly. It's about giving the AI the tools to interact with it, to literally reshape its perception to arrive at a better answer.
Okay, so today our mission is really to unpack the technical details. How does Thyme let these MLLMs autonomously generate and execute code? Code for image processing, code for complex math.
Right. It's a significant step, and hopefully this gives you, our listeners, a shortcut to being truly well-informed about the cutting edge of AI.
We'll dissect the how and the why behind this whole approach. We'll focus on the core technical mechanisms, the training strategies, which sound pretty clever, and what this might mean for future AI capabilities.
We'll try to connect the dots for you, helping you understand the important nuances of this research and its technical implications.
Okay, let's unpack this idea then. Thinking beyond images. We've seen MLLMs evolve so rapidly, we often hear them described as thinking with images, incorporating visual inputs into their reasoning process. That's been a massive advancement already, allowing models to interpret complex visual data. But what were the limits there? What were the bottlenecks in those previous approaches that Thyme is trying to overcome?
That's a great question to start with. Before Thyme, MLLMs tackling visual input beyond just basic recognition kind of fell into two main camps.
Okay.
One involved what they called thinking with generated images. So the model would actually create an image, maybe a diagram, maybe you would draw some auxiliary lines on something to help its reasoning.
Like sketching out a geometry problem.
Exactly. Useful for tasks needing imagination or, abstract visual aids. But the big technical limitation was the quality of those generated images. They often lacked the fine-grained detail needed.
So the generated image wasn't sharp enough.
Right. It could actually hinder the core visual perception task. If your generated helper image is blurry or imprecise, it's not really helping the model see the details in the original scene accurately. Plus, generating images is computationally really expensive.
High latency, I bet.
Huge inference latency, which, severely limited their use in real-time scenarios, which is critical for a lot of applications.
Okay, so that's one approach. Conceptually neat, but practically limited by quality and speed. What was the other category?
The second category was more about thinking with cropping. Here, the MLLMs were trained to identify relevant regions in an image, usually by outputting bounding box coordinates.
Right, seen that.
Then these regions would be cropped, maybe by an external tool, and processed further. Now, this strategy did help. It enhanced perception accuracy sometimes, helped mitigate hallucination, where models just make stuff up.
Yeah, that's a big problem.
But its functionality was really limited, pretty much just cropping via bounding boxes. That doesn't quite cut it compared to the multi-functionality we see in some advanced proprietary models, things that can do rotation, contrast, enhancement, even coding to manipulate images.
So cropping was useful for focus, but it didn't give the model a versatile toolkit for really interacting with the image.
Precisely. The earlier approaches were either, like you said, too high latency and low fidelity for detailed perception, or just too functionally restricted to dynamically interact with the image.
And that's exactly where Thyme comes in, right? With
Yeah.
its four core principles of autonomy. Let's start with the first one. Rich functionality.
Exactly. Time fundamentally shifts things. It moves from passive reception of visual info to active manipulation. So rich functionality means time is designed to do way more than just see.
Yeah.
It can perform a whole array of image operations. Cropping, sure, but also scaling, rotating, enhancing contrast,
Yeah.
and even doing complex mathematical computations based on the image.
Wow, okay. That's a much bigger toolkit.
Yeah. It's a significant expansion. Instead of just describing what's there, it can change what's there, or at least how it's presented, to better understand it or solve a problem. It gives the model agency over its visual input, treats images like dynamic data you can interrogate and transform.
And building right on that, the second principle, high autonomy. This is where, for me, it gets really interesting. Time decides if an operation is needed, what operation to use, and then executes it by dynamically generating code, all without a human stepping in for that specific task. It's like the AI is choosing its own tools from a toolbox.
That high autonomy is absolutely crucial. It's not just having the tools, it's having the intelligence to know when and how to use them effectively. Like a skilled craftsperson, right? They look at a job and just know which tool to grab and how to use it without needing step-by-step instructions.
Yeah.
And this raises a really important technical question. How do you enable a model to not just understand an image, but to know what manipulation is needed, and then execute that reliably with code?
It's more than seeing.
It's strategic visual problem solving. It needs a deep internal grasp of the task, the visual input's current state, and the potential impact of different operations. It's almost a metacognitive leap for these MLLMs.
Okay, third principle, efficient end-to-end training. This sounds huge for actually getting these things deployed. Thyme uses a two-stage process, supervised fine-tuning, SFT first, then reinforcement learning, RL.
Right.
And what's really remarkable, they say the SFT stage alone unlocks these core functions in just 200 GPU hours. That sounds incredibly efficient.
It is incredibly efficient.
Really?
Achieving that level of complex capability with that kind of training budget is, well, it's a testament to how clever their training methodology is. It speaks volumes about practical deployability.
I think it's much more accessible. And the fourth pillar.
Significant and stable performance gains. The paper shows Thyme consistently beating baselines across nearly 20 different benchmarks.
20.
Yeah, and it particularly shines in challenging tasks like high-resolution perception and complex reasoning. So it's not just a cool idea. It delivers measurable improvements in performance.
So the evaluation seems pretty comprehensive.
Very. Across a wide range of benchmarks, validating that these manipulation capabilities really do lead to better perception.
Okay.
And the ability to turn math problems into code really helps with reasoning benchmarks. And what's revolutionary here isn't just that it's better, but how it challenges that old idea that bigger models are always the answer.
Okay.
Thyme's strategic tool use gives it the sort of test time scaling ability. It lets smaller models, like the 7B one they used, punch way above their weight.
Okay, so how does Thyme actually do all this integration of vision and code?
Yeah.
You mentioned this dynamic interplay between the model and something called the sandbox.
That's right. The sandbox is a secure execution environment.
Like a safe space for the code to run.
Exactly. Imagine the AI isn't just chatting, but decides, hey, I need to run some Python code to figure this out. How does that model-sandbox relationship work?
Yeah, let's break down that pipeline.
Okay, so the pipeline is pretty elegant, really. It starts with the user input, a question, and an image. Then the MLLM goes into its reasoning mode. It analyzes the problem, and based on, the type of problem, how difficult it seems, it makes a key decision. Is code generation necessary here?
So it doesn't always generate code.
No. If the problem's simple, or maybe if previous operations in a conversation already solved it, the model just returns an answer directly. No code needed. Simple.
But if it's complex, that's where the sandbox comes in.
Precisely. If it needs more than a direct answer, the model autonomously generates executable code. And this isn't just one type of code. It could be for image manipulation, cropping, zooming, rotating, contrast adjustments.
All the things we mentioned.
Or it could be code for complex mathematical computations. And what's really impressive is the model itself decides the input parameters for these operations.
It figures out the coordinates to crop.
Okay.
Or the zoom level.
Exactly. It infers them based on the problem. There aren't external constraints forcing specific parameters. The model learns to figure it out.
Okay, so it writes the code, parameters and all. Then what? It doesn't just run inside the model, right?
No, and that's critical. The generated code gets sent to this external, secure sandbox environment for execution.
Well, external.
Security. Security is a huge part of it, yes. And resource management. The sandbox's main job is to safely handle that code and return the results.
And the results go back to the model.
Yes.
Yeah.
This isn't a one-shot deal. The execution results could be a processed image, a number, maybe even an error message if the code failed, are fed back to the model.
Ah, a feedback loop.
Exactly. The model uses these results for further reasoning in the next turn of the dialogue. This iterative process is crucial. It lets the model refine its approach, correct mistakes, perform multi-step problem solving, much like a human would.
That loop seems key for handling complexity. So this sandbox component is technically critical. It needs to be secure, robust. It's not just running any old Python script.
Absolutely. It's safeguarding the whole system while empowering the model.
Now, on the tech side, what kind of sandboxing tech are we talking about? Does the paper say? Is it containers, VMs? And what about the performance hit? Sandboxing isn't free computationally.
The paper doesn't explicitly name the specific sandboxing technology beyond saying it runs Python code and uses standard modules, but we can make some educated guesses. For this kind of secure, isolated execution, things like containerization, Docker, maybe lighter runtimes are very common in production AI.
Makes sense.
VMs offer even stronger isolation, but usually have more overhead, given they need efficiency, and mention that 10-second execution limit per snippet.
10 seconds, okay.
It's likely a balance, probably leaning towards containerized environments you can spin up and tear down quickly. And yes, there's always some performance overhead with isolation, but it's the necessary trade-off for system integrity. That 10-second limit was likely found empirically enough time for useful work, but prevents runaway code.
Okay, that makes sense. A practical limit. Beyond security, you mentioned the sandbox also helps the model with coding. It reduces the burden, especially for smaller models like the 7B one they used, which might not write perfect code every time.
Yeah, this part is really quite clever. It acknowledges that demanding flawless code from an MLLM, especially a smaller one, is maybe unrealistic. So the sandbox automatically handles some minor issues without changing the code's meaning.
How does it do that?
Well, for one, it uses Python's AutoPep 8 for code formatting. Basically, it cleans up messy code, fixing indentations, style issues, making sure it's syntactically valid, even if the model's output was a bit sloppy.
Like a built-in code beautifier.
Pretty much. It also does variable inference and adjustment, using Python's Atom module, which lets it analyze the code structure like reading its blueprint.
Abstract syntax trees.
Exactly. It can find variables. If the names contain box or chord, it assumes they're for cropping and automatically adjusts the values to fit within the image boundaries. This stops simple out-of-bounds errors.
That's smart. Prevents easy mistakes.
It's like the sandbox is the AI's patient code editor, tidying things up. It also presets common local variables like image path and imports necessary packages like CV2, OpenCV for vision tasks, before running the code, even if the model forgot the import statement.
So the code has the context it needs.
Right, and for multi-round conversations where code in one turn might depend on results from a previous turn, the sandbox records and incorporates all variables from previous executions. It maintains that historical context.
The model doesn't have to perfectly remember everything across code blocks.
The sandbox helps it remember, yeah. Maintains the state.
Okay, this is clever, as you said. But what are the implications of the model being a bit lazy on perfect syntax, relying on the sandbox fixes? Does that create a strong dependency, or is it just smart engineering a good trade-off?
I think it's definitely a smart engineering trade-off. Yes, it creates a dependency on the sandbox having these fixing capabilities, but that's not necessarily bad. In complex systems, modularity is good, right? Let the MLLM focus on the high-level reasoning. What code needs to run? Let the sandbox worry about the minor syntactic details or perfect boundary checks. This allows for faster development, lowers the bar for usable code generation from the model.
Frees up the model's capacity for the harder stuff.
Exactly. It implies that for many applications, it might be more efficient to have this intelligent wrapper or interpreter for the code rather than demanding absolute perfection from the generator itself. It makes the whole system more robust.
Okay, so the architecture relies on this model-sandbox symbiosis. But the magic behind Thyme's capabilities also lies in its two-stage training strategy. Supervised fine-tuning, SFT first, then reinforcement learning, RL.
Let's dig into the SFT phase, the cold start for building these abilities.
Right. The SFT phase is really the foundation, and it starts with this incredibly meticulous data construction pipeline. They mentioned leveraging over 4 million raw data sources.
4 million. Yeah, to curate a high-quality data set of about 500,000 samples in the end. A massive effort designed to cover a huge range of scenarios and task types to give the model a really broad understanding of when and how to use its new tools.
And the diversity of these scenarios seems key. They broke it down. First, there were no code generation scenarios, simple tasks where the model learns to just answer directly.
Exactly. It's crucial for the model to learn when not to use a tool, right? Avoid unnecessary overhead.
Makes sense.
Then they had real-world time data, about 50,000 question-answer pairs. These are samples that specifically need code, and they went through this rigorous verification process.
How rigorous?
First, run the code in the sandbox to ditch any non-executable stuff. Then use another MLLM, a powerful one, to check if the execution results actually make sense and help answer the question. And finally, manual expert screening to weed out anything ambiguous or low quality.
Oh, okay.
Yeah.
Multi-layered filtering. That sounds thorough.
Very thorough, ensuring high-quality data for these complex tasks.
And alongside that real-world data, they also manually constructed several specific data sets.
Yes, they called this manually constructed time data. This included specialized sets for cropping, teaching the model how to intelligently zoom into high-res images where details might be small. Also for rotation, addressing the fact that many MLLMs struggle with rotated images.
Because most training data has upright images.
Pretty much. So they generated rotated versions to teach reorientation. Also, data for low contrast enhancement, using OCR data to train the model to improve readability of faint text. And critically, data for computational code.
Turning math problems into Python.
Essentially, yeah. Transforming solutions from powerful models like Gemini 2.5 Pro, refining them with GPT-4o, into clean, executable Python snippets.
Okay.
Turning the MLLM into a calculator that understands visual problem setups.
That's quite a range. And they also included multi-round conversation data. You mentioned this teaches error correction.
Yes, this is vital. It means the model learns not just to perform an action, but to refine it. Maybe make a broad crop first, then a more precise one based on the result. Or even detect that a previous bounding box was wrong and fix it in a later step.
That addresses a common failure mode, right?
Yeah.
LM's propagating errors. If it makes a bad crop first, without this training, it might just stick with it.
Exactly. This multi-round data teaches it to self-correct, leverage history, vital for practical use. But you raise a good point. How robust is that correction, especially if the visual cues are really ambiguous?
Yeah, if the initial seeing part is way off, can it really recover just through dialogue?
That's an astute point. The robustness is still a challenge with highly ambiguous cues. The training helps with common fixable errors, refining a slightly off box. But if the model fundamentally misinterprets the scene or the image is so ambiguous a human would struggle, well, self-correction might still be limited. It still hinges on the model perceiving the error and reasoning about the fix.
So it helps, but it's not a magic bullet for deep ambiguity.
Probably not. The quality of the model's own explanation for why an adjustment is needed likely plays a role too.
Okay, so they've got this huge, carefully curated data set. How did they actually use it in the SFT phase? You mentioned some clever techniques to handle challenges. What was the first one?
A really crucial technique was to mask sandbox content. During training, they hide the actual output of the sandbox from the model's learning target
Why hide it?
to prevent gradient contamination. Think of it like this. If the model saw the sandbox's exact output, sandbox output marker and result, during training, it might just learn to memorize or predict those outputs directly. Cheat, basically.
Instead of learning the process.
Exactly. By masking it, they force the model to genuinely learn how to generate the code and how to reason from the results it gets back, not just copy the answer key.
Makes sense. What else?
Another strategy, train on last round only. For those multi-round conversations, they only calculate the training loss based on the final turn's logic and answer.
Why only the last round?
To stop the model learning inefficient patterns like make a suboptimal guess first, then correct it, they want it to learn the optimal reasoning path directly, which is usually represented in the final successful round.
Got it. Optimize for the efficient solution. They also looked at code comments, right?
Yes, and interestingly, ablation studies where they remove components to see the effect showed that removing code comments led to unsatisfactory results.
Even though comments aren't executed.
Right. It suggests the comments, by outlining the logic, actually help the model become more logical when generating the code. It's not just syntax, it's about the semantic intent the comments provide.
Fascinating. Like the comments act as internal reasoning prompts.
Something like that. And then there was math data annealing. This tackled the problem of the math dataset being much smaller than the image datasets.
Getting drowned out.
Yeah, potentially overwhelmed during training. So their strategy was, first, train on all the image-related data, then do a second fine-tuning stage exclusively on the math data using a lower learning rate.
A dedicated phase just for math coding.
Exactly. This activates the model's computational coding behavior, making sure it actually learns to generate code for math problems when needed, rather than ignoring that capability.
Wow, okay. That SFT stage involves some really intricate data work and training tricks. Seems essential for getting these abilities off the ground. Now, the second stage is reinforcement learning, RL.
Right. RL is often where models really learn to refine their decision-making, especially in complex situations, and boost their precision.
So how did they approach RL here? What kind of data did they use?
For the RL data construction, they went beyond public data sets and manually collected 10,000 high-resolution images. We're talking images wider or taller than 2048 pixels.
High res, okay. Why?
The focus was specifically on images containing challenging objects, particularly small ones, things occupying less than 5% of the total image resolution.
Tiny details.
Exactly. Human annotators then crafted specific questions for these images, covering things like OCR, attribute recognition, position, quantity, object recognition, chart understanding. Basically, tasks that force the model to deal with these small, hard-to-see elements. This really pushes the model's perceptual limits.
I can see how finding and interpreting something taking up less than 5% of a huge image would be tough. Like finding a needle in a haystack, visually. What are the specific technical hurdles there, and how does RL help?
The main hurdle with these tiny objects is that traditional vision processing, even in MLLMs, often involves downsampling the image. This can just erase the features of small objects or blend them into the background noise, leads to misdetections or hallucinations.
So the detail gets lost.
Right. The RL phase tackles this by essentially increasing the difficulty with the specific high-res small object data. By repeatedly exposing the model to situations where it must use tools like cropping and zooming to resolve these tiny details, the RL process reinforces that behavior.
The rewards push it to zoom.
Exactly. The reward function, which we'll get to, would heavily penalize wrong answers on these tasks. This forces the model to learn the precise invocation of code needed for that visual manipulation. The RL fine-tuning makes it learn. Okay, for this kind of question, on this kind of image, zooming here is the rewarded action.
Got it. So it learns the strategy through reward. Now, a key part of their RL was this algorithm, GRPO with adaptive temperature sampling, GRPO ATS. Sounds complex, but you mentioned it was a big breakthrough.
Absolutely critical, yes. GRPO stands for Guided Policy Optimization, an RL framework. The ATS, adaptive temperature sampling, is their key innovation here, and it came from tackling a core conflict.
What conflict?
Code generation needs precision. Even one wrong character can break it. But natural language generation often benefits from exploration, being a bit more creative and random, which you get with higher sampling temperatures.
Ah, so high temperature is good for creative text, but bad for functional code.
Exactly. High temperature for code leads to unusable garbage, invalid characters, syntax errors. The code just won't run.
So what does GRPO ATS do?
It implements an adaptive temperature. It watches for the special code token that signals the start of code generation. When that appears, boom, the sampling temperature instantly drops to 0.0.
Zero, so completely deterministic output.
Completely deterministic for the code part. Ensures it's syntactically valid, executable. But for the natural language reasoning parts before or after the code, the temperature stays at 1.0, encouraging exploration and better reasoning.
That's really elegant, adjusting on the fly based on context.
It is, and it has two big benefits. One, improves sample efficiency in RL because it stops wasting time generating broken code during training rollouts. Two, it prevents code avoidance.
Code avoidance.
Yeah, if generating code is often error-prone and leads to low rewards, the model might just learn to avoid generating code altogether, even when it's needed. By making code generation reliable with ATS, this isn't an issue.
That makes a lot of sense. Super clever. But okay, GRPO ATS ensures the code is syntactically correct, executable. How does it make sure the code is semantically correct does the right thing. What if it writes perfect code to crop the wrong part of the image?
That's a crucial distinction, you're right. grpoats primarily gets the syntax right. It makes sure the code runs, ensuring it does the right job for the problem's semantic correctness that's mainly handled by the reward function design.
Ah, the rewards guide the meaning.
Exactly. If the model generates perfect cropping code, but it crops the wrong area, the subsequent reasoning will likely be flawed, leading to a wrong final answer. The reward function components, especially result reward and consistency reward, will assign a low score to that whole attempt.
So the model learns, okay, that code ran, but it didn't help. Bad path.
Precisely. grpoats provides usable tools. The reward function teaches the model how to use them effectively.
Got it. Clear separation of concerns. Beyond ATS, they also did some sampling optimization to stop repetitive errors.
Yeah, a couple of things. One is an early termination mechanism. They use the Rabenkarp rolling hash algorithm, which is really efficient for finding repeating patterns in strings.
Like detecting copy-paste.
Sort of, yeah. It detects repetitive substrings in the model's output. If the total length of these repetitions gets too high, they used a threshold of 50% of the total output. It just stops the sampling for that attempt.
Why?
To avoid wasting compute cycles on models getting stuck in a loop, just repeating the same nonsense over and over, which can happen in RL.
A sanity check, basically.
Pretty much. They also impose a hard cap on the maximum dialogue turns, max iterations, to keep context length manageable and improve training efficiency.
Okay, these seem like practical optimizations. But that early termination, could it ever cut off a genuinely useful iterative process? Like, if the model was making small, similar adjustments repeatedly to zero in on something, is 50% repetition always bad?
That's a fair point. Any early termination has that risk. A truly subtle, iterative refinement might look repetitive to a simple algorithm. However, the 50% threshold seems quite high. It's likely targeting really egregious loops, not minor variations.
So it's probably catching the obviously broken cases.
Probably. And the max iterations cap is a blunt tool, but necessary for practical training. It's often a trade-off. Accept a small risk of cutting off a rare, valid, long process to gain huge efficiency by stopping common failure modes quickly.
Makes sense.
Yeah.
Okay, let's talk reward function design. This is how the model learns what's good or bad during RL. What were the key pieces they put together?
The reward function is absolutely critical for shaping behavior. They had several components. First, a formatting reward. This encourages the model to output its response in a specific structure. Think reasoning block followed by answer block.
Just for neatness.
Not just neatness. It improves interpretability and forces the model to explicitly show its reasoning before giving the final answer. Helps understand why it reached a conclusion.
Okay, that's useful.
Second, the result reward. This is the core correctness check. Does the model's final answer match the ground truth? They used a hybrid approach here. Simple rule-based matching for things like numbers or specific keywords. If that doesn't work, or for more open-ended answers, they use another powerful MLLM as a judge to check for semantic equivalence.
Using an AI to judge another AI's answer. Okay.
Yeah, becoming more common, allows evaluating more complex, nuanced answers.
And then there was a consistency reward. Sounds important for logic.
It is. This checks if the final answer actually follows logically from the reasoning steps presented in the think block. Again, they use an auxiliary MLLM to assess the coherence between, say, the last 500 characters of reasoning and the final answer.
So does the thinking actually support the answer?
Exactly.
Yeah.
But here's a really clever innovation in how they combine these. You could imagine a scenario where the model gives a wrong answer, but provides perfectly consistent reasoning for that wrong answer.
Right. Logically consistent nonsense.
Yeah, precisely. To avoid rewarding that, their final reward formula applies the consistency bonus only if the result reward indicates the answer is correct. The formula looks something like result reward x 1 plus 0.5 die consistency reward plus 0.5 die formatting reward. That multiplier, 1 plus 0.5 consistency, only kicks in if result reward is positive.
Ah, so consistency only boosts the score if you're already right. That's smart. Prevents rewarding confident failure.
Exactly. A very important nuance in reward design.
The ablation studies on these rewards were interesting too. Consistency helped. But they tried other rewards, like a process reward for just the quality of the syncing text, and a code reward for just successfully running code. And those didn't help. Sometimes even hurt performance.
Yeah, those results are super informative about the art of reward design. The failure of the process reward suggests it's just really hard to objectively quantify good reasoning in text form. It's subjective. A model might learn to generate text that looks logical but isn't actually helpful, or just becomes overly verbose to game the reward.
Hard to measure good thinking.
Very. And the code reward failure is also telling. Rewarding the mere act of generating successful code, regardless of whether it was needed or useful, led the model to sometimes generate pointless code, like cropping an already clear image or using Python to add 2 plus 2 adds overhead, no benefit.
So it encouraged busy work.
Pretty much. It highlights that rewarding the outcome, correct answer, and the logical link between reasoning and outcome is much more effective than trying to score intermediate steps objectively or rewarding actions divorced from their utility. It's the so what of the code that matters.
Okay, so we've covered the architecture, the data, the complex SFT and RL training.
Mhm.
After all that, what did Thyme actually achieve? The paper has extensive experiments, right? Nearly 20 benchmarks.
Yeah, the results are genuinely quite striking. Looking at perception tasks, the Thyme model, even the 7 billion parameter version, showed significant advantages over much larger baseline models, even a 32 billion parameter one in some cases.
Smaller model doing better.
It highlights that just throwing more parameters at a problem doesn't automatically solve complex perception. Thyme's strategy of test time scaling, actively manipulating the image at inference time, is incredibly effective. For instance, on benchmarks focused on real-world scenarios like monitoring or autonomous driving.
Critical areas.
Right. Where the baseline 7B model struggled, Thyme showed perception improvements of over 25%, and reasoning improvements sometimes hitting 30% to 80%. These aren't small gains. They're substantial leaps in challenging domains.
Wow. That really underscores your earlier point about how the model interacts, being as important as its raw phi's. What about reasoning tasks?
There, too, Thyme showed notable gains. By converting complex calculations into executable code, it not only gets the math right more often, but also seems to improve the visual recognition needed to set up the problem. And it avoids having to do super complex multi-step calculations purely internally, which can be error-prone.
Offloads the hard math to the reliable sandbox.
Basically, yes. And across general tasks, because it's better at both perception and reasoning, Thyme shows significant overall gains. One key benefit they highlight is a substantial reduction in hallucination.
Making stuff up less often.
Exactly. Because it can actively check and manipulate the visual input, its answers are better grounded in the actual image content, a big step towards more reliable AI.
These results are impressive. It really does feel like a shift. It makes you wonder if MLLMs can do this autonomously, manipulate visuals, run calculations. What does that mean for them acting as, say, digital engineers or scientific assistants?
It's a great question. We're definitely moving towards MLMs that are less like passive interpreters and more like active participants in problem solving. They can perform this sort of mini scientific method, observe, image question, hypothesize what operation is needed, experiment, generate a run code, analyze results.
A closed loop of inquiry.
Right. This ability pushes them beyond just being assistants. They become potential collaborators, tackling tasks that previously needed a human using specialized software. Think about fields like engineering design, material science, medical image analysis.
Yeah.
This could really change things.
Let's make it concrete. The paper has examples, right? Illustrative case studies. What did they show for cropping and zooming?
Yeah, some great examples. One shows Thyme looking at a street view image with a tiny distance sign. It figures out it needs to zoom, generates Python code to crop and zoom just that sign, and then accurately reads Michigan.
Wow. From illegible to readable through code.
Exactly. Another example, extracting a phone number 206-441-5000 from a sign on a building again, precise cropping and zooming did the trick. And even more nuanced, looking at a complex aerial image, it was asked if there were awning tricycles in a specific area, zoomed in and correctly determined their absence.
So it's not just finding things, but confirming they aren't there. That requires careful checking.
Definitely. Shows a deeper level of perception. Then for rotation and contrast enhancement, one example shows it taking a slanted image of a mathematical formula.
Hard to read sideways.
Right. It generates code to rotate the image correctly, making the numbers 0.642857 clearly legible, and then even represents the formula in LaTeX format.
Very practical for digitizing documents or notes.
Absolutely. Another shows it tackling a low-contrast image with faint text. It generates code to enhance the contrast, allowing it to clearly identify the word communities. Great for OCR on degraded documents.
And it handles complex calculations too, not just visual stuff.
Yes. One example involved a physics-style problem presented visually, maybe with a diagram and data points, following a formula TM. Thyme had to figure out the constants A and B.
How to do that?
It deduced the mathematical steps needed involving logarithms and powers and generated Python code to perform the calculations using the given data points. It correctly calculated A as roughly 1.68 and B as 0.45.
So it combined visual understanding of the problem setup with generating the correct mathematical code.
Precisely. These cases really showcase that active problem-solving leap. But, this process reasoning, generating code, sending to sandbox, getting results back, it can't be instantaneous. What about the latency? How fast is this? Could it work in real time? That's a critical, practical question. The paper doesn't give specific latency numbers per operation, but it does mention that 10-second sandbox execution limit per code snippet.
Right.
So each cycle of code generation and execution could take up to 10 seconds, plus the model's own thinking time. For applications needing true real-time responses, like maybe autonomous driving reacting to something unexpected, or live video analysis, multi-second latency is usually too slow.
So maybe not for high-speed robotics yet.
Probably not in its current form for highly time-sensitive loops. The current latency profile, especially if it involves multiple rounds of interaction, seems more suited for tasks where a human is involved and can tolerate a few seconds of processing. Things like data analysis, scientific research assistance, detailed image forensics.
Where accuracy is more important than sub-second speed.
Exactly. Reducing this latency faster sandbox, more efficient code generation would be a key hurdle for deploying Thyme in those really demanding real-time scenarios.
Makes sense.
Mm-hmm.
Latency is always the engineering challenge. Now, credit to the researchers, they also included bad cases, examples where Thyme didn't perform perfectly. These are often super insightful.
Absolutely. Learning from failures is crucial. One category was complex problems without coding. They showed an example with a chart of machinery occupancy rates. Despite it being high resolution, Thyme just tried to answer directly without cropping or zooming.
And got it wrong.
Yeah, it potentially missed key details and misidentified which machine had the highest occupancy. It suggests the decision-making module when to use a tool isn't foolproof. It might fail to use a tool when it should have.
Okay, what else went wrong?
Another category was unuseful coding, basically the opposite problem, generating code when it wasn't needed, like using Python for a trivial calculation like 7/8, adding unnecessary overhead, or even making errors in the simple code, like confusing variables in a basic trigonometry problem.
So sometimes too eager to code, sometimes not eager enough, and sometimes messes up the code.
Right. And the last one was inaccurate cropping. An example showed it trying to read a train's model number. It generated cropping code, but the cropped region was slightly off, maybe including irrelevant background. Even if it somehow got the final answer right in that case, the process was flawed. It shows persistent challenges in precise object localization, knowing exactly where to zoom.
These bad cases are really telling.
Yeah.
It seems the core challenge is still that meta-reasoning layer, right? Knowing when and how to use the tools most effectively. How could they improve that? Maybe tweak the reward functions more, penalize useless code.
I think that's exactly it. These failures point to needing a more sophisticated self-reflection capability. The model needs to get better at assessing problem complexity and predicting the actual utility of using a specific tool before committing to it.
Like estimating the value of information from a zoom?
Something like that. Maybe explicit meta-learning, training the model to predict the outcome or reward change if it were to use a tool. For rewards, yeah, you could introduce a cost for coding a small negative reward for invoking the sandbox, which needs to be outweighed by a significant correctness reward.
Discourage frivolous coding.
Right. And for inaccurate cropping, maybe the consistency reward needs to be stricter. Penalize reasoning based on flawed visual manipulation, even if the final answer happens to be right by luck. Force the model to be accurate and efficient in its tool use, not just lucky.
Okay, so wrapping up this deep dive, it feels clear that Thyme isn't just another incremental update to MLLMs. It really represents a potential paradigm shift, moving from AI understanding images to AI interacting with images and solving problems using code. It writes itself.
I agree. It successfully blends autonomous code generation for both visual manipulation and complex computation. The two-stage SFT and RL training, especially powered by that clever GRPO ATS algorithm.
The adaptive temperature thing.
Right. That dynamic adjustment for code versus text generation is a particularly elegant solution to a really tricky technical problem. It paves the way for much more versatile and capable AI.
But like all cutting-edge research, it has limitations. And these often point towards the next exciting research directions.
Definitely. The paper itself highlights a couple of key ones. First is model capability. They openly acknowledge that Thyme's overall performance is still tied to the strengths and weaknesses of its base foundation model.
Garbage in, garbage out. Or rather, limited base model, limited time performance.
Pretty much. If the underlying MLLM struggles with precise object localization or isn't great at generating complex but correct code, then Thyme will inherit those limitations. It might make inaccurate crops or generate buggy code sometimes.
So building time on top of even more powerful future foundation models could unlock even better performance.
That's the implication, yes. Stronger foundations should lead to more reliable and accurate tool use.
What's the other main limitation?
The valuation scope. This is a common challenge in fast-moving fields. There's currently a lack of standardized benchmarks specifically designed to test these advanced image manipulation capabilities, things like rotation correction or low contrast enhancement.
Most existing benchmarks use clean, well-oriented images.
Largely, yes. They focus on standard object recognition or VQA on relatively high-quality images. So while Thyme can perform these advanced manipulations, it's hard to robustly quantify how well it does them compared to other methods simply because the specific test datasets don't exist yet.
We need new benchmarks to measure these new capabilities.
Exactly. It's an ongoing cycle in AI research.
So this leads to a final thought maybe for you, the listener. As MLLMs gain these autonomous capabilities, moving beyond passive observers to become active manipulators and calculators, how might this change how we approach complex data analysis or even scientific discovery?
Yeah. Could these models become truly indispensable partners? In fields needing both sharp visual perception and precise computation, could they fundamentally alter the speed and even the nature of research itself?
It's a powerful idea, isn't it? AI that can literally reframe a visual problem by manipulating the input and then solve the resulting numerical problem with code it generates on the fly. A future vision that seems to be arriving very quickly.
It certainly feels that way.
Well, that's all the time we have for this fascinating look at Thyme. Thanks for joining us for this deep dive.